Yeah, good afternoon. So we'll wait just for another few seconds or maybe a minute to give people a chance to join the meeting. We can start sharing. Yeah, so we maybe start smoothly, let's say. So yeah, let me give you a warm welcome, first of all, to this installment of the European Microwave Association's webinar series. So my name is Jan Borowski. I'm with the University of Bochum in Germany. And yeah, I'm here today on behalf of EuMA and have the pleasure to host this meeting, this webinar, where we'll have Carlos Juan in a few seconds, giving us a very interesting talk about yeah, microwaves in medical applications and biomarkers. And yeah, before we start, I would just take the chance to yeah, give a very rough introduction to the series and to the European Microwave Association for those of you who are maybe not that familiar already with us. Yeah, so that's the advertisement for today. So just give me a few seconds before we have Carlos giving his talk. Yeah, if you're interested in microwaves and yeah, instrumentation and measurements in general, let's say, you can find the other events of our webinar series on our YouTube channel, for example. To just go to your favorite search engine and look for EuMA and webinar series, and I'm sure you will find them. So that's quite a broad range of topics that we have available right now. Yeah, and given that the deadline is approaching, I would just take the chance to do some more advertisements for the European Microwave Week, which is a major microwave-related event in Europe. So it's a full week covering 3 microwave-related conferences: the EuMIC, the European Microwave Integrated Circuit Conference, the UMC, the European Microwave Conference, and the EURED, the European Radar Conference, all in the same location. And this year we will be in London, in the UK, at the beginning of October. So I will surely be there. Hope to see a lot of you there as well. For those of you who are graduate or undergraduate students or doctoral students, there are also dedicated events, so like schools on specific topics in microelectronic designs, for example, or we also already had a radar school. So just look out for the program. It will surely be interesting. Together with IEEE, there are joint young professional events on the weekend before the week usually. And there will be for sure a career platform as well. And yeah, for those of you who are yeah, already part, let's say, of the scientific community, yeah, and have some spare time at the in the next few days, there will be the deadline for paper submission on Friday this week. So if you plan to make a contribution, have this in mind. Yeah, for those of you who are students and still want to get a chance to get a funded experience there, let's say, there's a chance to become a student volunteer, which basically means that you have 2 or 3 days of service. That depends on the number of applicants. And yeah, you do some helping tasks in organization there at the event, for example, yeah, room control, badge scanning, these kind of things, but also help with your registration, for example. And in exchange, you usually get the chance to get yeah, support in hotel stays, for example, and you of course have the chance to visit the whole conference without any attendance fee. So for those of you who are enrolled students, that's a great opportunity. look out for this as well. And here's the deadline will be in June, so that is a bit more relaxed to think about. Yeah, and that's it with the advertisement blog. So I'm very happy to have Gabriel Juan here with me today, who will give a talk on microwave sensors for non-invasive biomarkers detection. Yeah, and I guess about the talk, Carlos will tell himself what is behind this. Yeah, so I had a look at his CV, and it's really impressive. So I like to I need to shorten it a bit, Carlos. Sorry for that. So you received the master's and the PhD degree in electronics engineering from Miguel Hernández University in Spain in 2014 and 19, and yeah, there you joined the neuroengineering biomedical research group as a fellow. But not only that, Carlos was a visiting researcher with several groups, let's say. He was with Lab SDICC in the Bretagne. He was an adjunct professor with the departments of material science, optics, and electronic technology in Spain. He had several postdoctoral research fellowships, also with medical robotics group in Malaga in Spain, for example, but also with Technical University of Cartagena. Since September 2024, he's a senior research fellow with the Institute of Bioengineering. And besides that, he's very active in our international community, let's say. He has been he received the Outstanding Associate Editor Award in 23 and 24 for his service in the IEEE transaction, instrumentation, and measurements. And he currently is associate editor-in-chief for this transaction as well. And since 25, he's an IEEE IMS distinguished lecturer. So, Carlos, with that, I'll end this, even though there would be more to tell. And yeah, I'm looking forward to your talk. Yeah, go ahead.
Okay. Okay, thank you very much for this nice introduction. So I will share my screen. And all right, you should be seeing my screen.
Yeah, that's good. So
okay, so well, as I said, thank you very much for this nice introduction. I am very happy to be here sharing this time with you. I hope you will enjoy this lecture. Today, I would like to talk about the use of microwave sensors for non-invasive biomarkers detection. It is important to note that while the applications are wide, today I will focus on a particular application, which is glucose concentration detection for interest for example, diabetes, which has several particularities. So we will see maybe a different sensing approach, which I think is more instructive. So let's get started. This is the plan I propose for today. First of all, I will describe the sensing principle and the dielectric relaxation, which is the physics underlying the measurement paradigm that we will explain. And then I will discuss how can we use microwave resonators as sensors, particularly as dielectric permittivity sensors. Then in the point number 3, I will underscore the sensing approach I want to highlight today. That is the sensors based on the unloaded quality factor changes. Those are for particular interest for glucose measurement. And at the end of the lecture, I will finish sharing with you some examples of studies, recent studies that have been published using this sensing approach. So to start, the first thing we need to ask ourselves is what happens when an electric field is applied to a piece of matter? How is this interaction between the material and the electric field? Well, indeed, the response to this question depends on whether the charges in the material are free or if they are bound, forming dipoles. The dipoles could be permanent or induced, okay? We are not entering into that. But if the charges are free, when the electric field is applied, what we'll have is a displacement of the charges following the direction of the field. And this displacement of the charges leads to an electrical conductivity. However, if we have a system of dipoles, because we have a dipolar material, the chargers are bound, they cannot displace. They cannot move, they cannot change the position, but they can rotate. So when the field is applied, the dipoles will rotate to align parallel to the direction of the field. The result of this rotation in the macroscopic view is a permittivity, what we call the permittivity, which is a complex parameter. It has real part and the imaginary part. Okay, so we had two different effects depending on the type of charges, the type of molecules, atoms that we have into this material when we apply an electric field. Now, the interesting thing is that both magnitudes, the conductivity and the complex permittivity, both depend on the medium composition. They depend on the type of charges that we have in the medium. And this means that studying the dielectric spectrum is useful for analyzing the composition of the medium. Characterizing the values of the conductivity and the complex permittivity for each material, for each frequency, allows us to obtain the composition of this material, the type of charges, atoms, molecules that there were inside this material. And thanks to this reason, we can propose the use of complex permittivity sensors as composition sensors to indirectly identify the chemical composition of any material by looking into the changes in the complex permittivity of the material with sensors tuned to be sensitive to changes in this permittivity. So let's see this with a more graphical way. Imagine that we have a dipolar piece of matter, a system of dipoles, such as, for example, water, pure water, okay? In the absence of field, if there was no field, the dipoles will align randomly due to thermal motion with no macroscopic charge. But what happens when we suddenly apply an electric field that is traveling through the material? The result is that the dipoles will rotate, okay, rotate in order to align parallel to the direction of the field. They will rotate so that they align parallel to the direction of the field. Okay, now let's go into the next level. Now imagine that we apply a varying field, a field that is pointing to different direction at each moment. It's pointing right, left, right, left, right, left at a constant frequency. What do you think will happen? Well, in this case, the result is a constant rotation of the dipoles that will try to align parallel to the direction of the field at each moment. And if the field keeps on changing its direction, the dipoles will keep on rotating in order to align parallel to the direction of the field. And now let's go to the last level. Imagine that we apply a new electric field with varying direction, that is with varying frequency, and the frequency of the field is increasing and increasing and increasing up to infinity. This time, the field is changing its direction from right to left, but at an increasing speed, so that it goes to right, left, right, left, right, left, right, left, right, left, right, left, so that the frequency of the field is increasing and increasing and increasing. This time, the result will be, again, a constant rotation of the dipole with an increasing angular speed. So the rotation will be faster and faster and faster and faster and faster and faster and faster. But do you think this behavior can be kept up to infinity? Well, the answer is no. There should be a limit. There must be a limit for the dipoles. Currently, we can increase the frequency of the field up to insane values. We have technologies for that. But matter is matter, dipoles are dipoles, and dipoles have their limitations. So there will be a moment in which we will be able to increase more the frequency of the field, but the dipoles will reach their maximum rotation speed. at that moment, if we keep on increasing the frequency of the field, the dipoles will no longer be available to rotate faster. So they no longer be available to follow the fast variations of the field. At that moment, the dipoles will no longer feel the field. They will no longer see the field. And they will go back to the previous state. The dipoles will align randomly again, even if the field is still present. We are still applying a field, but there is no effect on the dipoles due to the high frequency. This process is what we call the dielectric relaxation. The dipoles just relaxed and stopped following the directions of the field because they simply cannot follow the fast variations of the field. So this is a very interesting phenomena and very useful phenomena, and it has been characterized and defined from a mathematical point of view. In the microwave region, we know that the dielectric properties of materials are dominated by relaxation processes. There are several relaxations occurring at different frequencies. And these relaxation processes are useful to obtain information about the medium compositions. As we can see here, for example, we have a simple mathematical model to define these relaxations. This is the so-called Debye model, I would say the most well-known model for dielectric relaxation. However, it's not the only one. There are other models like Cole model, Cole-Debye models, and some other more complex models. However, this is the basic one, and in most cases, it's enough for a good description of what we are really seeing in the experimental trials. In this model, as a convention, the complex relative permittivity is defined as a real part minus an imaginary part. Of course, both parts are frequency dependent, and the complex relative permittivity is frequency dependent because it is logical that the value of the permittivity, which depend on the frequency of the field, and it will depend on whether the dipoles are able to follow the variations of the field or not. The permittivity is also defined as a relative permittivity relative to the permittivity in vacuum, also as a convention. And well, in order to define this behavior with these relaxations, the Debye model proposes a permittivity, a value of the permittivity in the infinite frequency plus a sum of the different relaxations that occur at different frequencies, in addition to the conductivity at static frequency. So this is how we define this from a mathematical point of view. And now we will be interested to analyze what happens in frequencies very close to the relaxation. If this is the frequency of the relaxation, what we will see is for the real part, there will be a sudden decrease from high values, the values at the static frequencies, towards low values, the values at infinite frequencies. And for the imaginary part, we will have low values, and as we are getting closer to the dielectric relaxation, we will have a sudden increase of the values of the imaginary part, followed by a sudden decrease at frequencies higher than the relaxation. So during the relaxation, looking into the real part of the permittivity, the material evolves from being highly polarized when the dipoles are following the variations of the field to weakly polarized after the relaxation when the dipoles no longer follow the variations of the field. And the imaginary part, which is associated with the losses, the dielectric losses, will have a sudden increase during the relaxation and the frequencies nearby. So we can expect an increase of the losses near the relaxations, near any dielectric relaxation. In this point, we will define the loss tangent as the quotient between the imaginary part and the real part of the permittivity. And now that we understood this sensing principle, we understood what is the relative permittivity and what information can we obtain from it. Now we are interested in measuring this permittivity from any material. To do that, the options are wide. We have plenty of options depending on the requirements of our application and the frequency range we are interested in. We can have broadband methods, such as, for example, impedance spectroscopy, coaxial proofs, transmission reflection line methods, and so on and so forth. But today, I would like to bring to your attention the use of microwave resonators. By paying the price of having information only in a narrow frequency range, usually in one frequency point, by paying this cost, we will be able to make measurements with materials under test that have very low sizes. This is really interesting, particularly for biomedical applications where the availability of the sample is really limited. And also, one of the most interesting features is that these sensors allow us to make non-invasive measurements. We are not really talking about remote measurements because we cannot do it at a high distance, at a long distance. But in close distances, we can measurements through small walls, through a thin layer, or even through the skin. So these two features, the possibility of making measurements with very small sizes of the sample and the possibility of making non-invasive measurements, are good enough to propose the use of microresonators, at least for the biomedical domain. They have obviously other applications in other industry fields, but today we will be focused on the biomedical domain. So let's have a look into the theoretical part of a microwave resonator. As any resonator, it can be defined with a simple RLC circuit, parallel or series. In this case, I took the parallel one. So we are interested in obtaining the input admittance of the RLC circuit. It can be easily obtained, and we can see that it depends. It is a complex parameter with real part and imaginary part, and it will have a pure real part that is defined by the conductance, the inverse of the resistance. This conductance will give us the pure real part, and then it will have an imaginary part with two contributions: a positive contributions due to the capacitance, and a negative contribution due to the inductance. Looking into this response, it is easy to see that if we only consider the imaginary part, there will be a frequency at which the positive contribution in the imaginary part will compensate the negative contribution of the imaginary part. There will be a frequency that will satisfy omega c equals to 1 over omega L. At this frequency, and only at this frequency, the imaginary part will be 0. And the input admittance will be purely real, only real. Also, the modulus of the input admittance at this frequency will be minimum, since the second contribution will be 0. Here we can see the plot of the modulus of the input admittance depending on the frequency, and we can see here that for a given frequency that we call the resonance frequency, the amplitude of this modulus is minimum and equals to G, the conductance. And then we can define other parameters such as the bandwidth. It is easy to calculate which frequency is this one, and the result is this expression here, 1 over 2 pi square root of L times C. And we can compute other parameters such as bandwidth or quality factor. Here we can see the associated plot of this circuit in terms of the S11 parameter, the reflection parameter. Again, at the resonance frequency, there must be a minimum of the response, and the peak will be sharper or wider depending on the value of the bandwidth and quality factor. So, as we can see here, this resonance frequency depends on the values of the inductance and the capacitance. This means that if we see variations in the resonance frequency, we can obtain the new values for the capacitance or the inductance, and the same looking at the quality factor or the bandwidth. So by now, we have a capacitance sensor or an inductance sensor. If we go for a more sophisticated model, such as a transmission line model, we will have a similar behavior, but this time we no longer have a lumped capacitance or lumped inductance, but we have distributed elements. In this case, the response is defined by the intrinsic parameters of the line, such as the intrinsic capacitance and the attenuation and propagation constant. And we will have, again, a resonance frequency that will depend on these parameters. But these times, these parameters depend on what we call the effective permittivity. And the effective permittivity is a combination between the permittivity of the substrate, which is fixed, and the permittivity of the materials that are upon the substrate in the upper space of the circuit. Usually, in conventional microwave design, we consider air as the material that is in the upper volume. But if we change this and we put some material just upon the circuit, we will have a permittivity that will be varying depending on the permittivity of the material. And therefore, the intrinsic parameters of the line will be varying, and therefore the resonance frequency, quality factor, and so on will be varying depending on the permittivity of the material. And this is how we can use these circuits as permittivity sensors. Now, to sum up, at microwave frequencies, we have that the material under test size can be comparable to the wavelength, which is really small. And we also know that the dielectric relaxation processes of water, and therefore of most biological systems, are covered within the microwave regime, particularly between 2 and 20, 21 gigahertz, depending also on the temperature. And this is why we can state that microwave technology allows to investigate the effects of dissolved species on such relaxation. We can analyze the composition of water or any biological liquid, such as, for example, blood, using this technology. It is not easy, okay, but we can do it. Now, let's go for the final model, the full wave model of the resonator. Again, we have here the comparison with the lumped element model. We even removed the resistance just for brevity. We have a resonance peak that depends, again, the resonance frequency and quality factor as a function of the values of the lumped inductance and lumped capacitance. If we go for full wave model, this time it is an open loop resonator, a split ring resonator. We have the ground plane here, and here we have one of the arms of the resonator, and here the other arm of the resonator. We will see, if we plot the field lines, that they will travel through the substrate towards the ground plane, but they will travel also in the material in the upper volume of the substrate from one arm to the other arm. Here we put, for simplicity, just a small container in gray filled with the liquid in blue. And we can see here how the electric field lines are traveling through the container and also through the liquid. So the effective permittivity will change depending on the permittivity of the liquid. If we change the liquid and we use different liquids for different measurements, we will be able to see changes in the response, changes in the resonance frequency, changes in the maximum of amplitude, changes in the bandwidth, changes in the quality factor that will depend on the permittivity of the sample. And please note that in this drawing here, the liquid is never touching the circuit. So you have the bottom of the container between the circuit and the liquid. So you can change this bottom of the container by the skin, and you will see the example of measurement in blood through the skin, a non-invasive measurement without direct touch of blood. So now let's focus on the particular application I wanted to show today, the glucose measurement. How can we apply this to glucose measurement? Well, I propose to make a very simple experiment just by simulations. These simulations were made with ANSYS HFSS software, but they can be made with CST Studio or with any other full wave software. They are very simple simulations. For this case, I selected a substrate with permittivity of 6.0 and loss tangent of 0.02, and I designed a simple open loop resonator here with two input-output lines tuned at 50 ohms. I designed the length of the resonator in order to resonate at 9.2 gigahertz when there is no sample. It means when there is only air in the upper volume. It is very easy to tune the resonator with the formula for having your desired resonance frequency. And in addition to that, I included a block for simulating the sample. It is only just a block, a solid block, and I will change the properties of this block to simulate the variations in the sample. Particularly, I will be running simulations with different values for the real part of the permittivity and for the loss tangent. You can run these simulations and then you can retrieve the simulated response of the resonator for each simulation. And from each one, just for brevity, I reduce the analysis only to two parameters. For each simulated response, I computed the resonance frequency and I computed the unloaded quality factor. And then I plotted all the resonance frequencies against the corresponding values of the real part of the permittivity of the sample and all the quality factor against the corresponding values of the loss tangent. And this is the result for both parameters. Now, here we should analyze these plots and we can easily identify the interesting regions. If we want to make a sensor, we are really interested in regions like this one with a very sharp slope. In other words, if we want to use the resonance frequency of the measurement parameter, we are interested in having samples with very low values of the real part of the permittivity, values between 0 and I would say 5, 6, maybe 7. Because in this range, we are sure that a very small variation in the permittivity of the sample will be seen as a notable variation in the resonance frequency of our sensor. So this region here does not seem interesting at all, but this region seems very interesting for our purposes. And we can say exactly the same for the unloaded quality factor. We will be interested in measuring samples with values of the loss tangent in this region between 0 and 0.1, more or less, even up to 0.15 or something like that, okay? So now we need to analyze what are the values of the real part of the permittivity and the loss tangent of the samples we want to measure. To do that, we can go for an application of measurement of glucose in blood, or as a simplified step, I did it for measurement of glucose concentration in water, in pure water. This is a simplification, but it's not a bad simplification because human blood is made 80% of water. So finally, the dielectric properties of human blood are not so far from the properties of water. We should take pure water and we should make the permittivity, measure the permittivity of pure water with other techniques such as coaxial proof, for example. Fortunately, water is one of the most studied elements in history, maybe the most studied one, and some other researchers did this work for us. So we can easily go to the literature and find comprehensive dielectric characterizations of water for different atmospheric pressures, for different temperatures, and for a lot of conditions. I selected one of them, one of the most well-known of them, and this is the result. Okay. These are not good news. As you can see, well, it does not seem a very good idea to make measurements with this sensing curve. This is more or less the region for the dielectric properties for the real part of the permittivity of water at 25 degrees, about 75, 76. So this is really not a good option if we want to make measurements of any component dissolved in water with this design. Please note that this does not mean that the resonance frequency is not a good option for these sensors. It is really a good option for other applications or with other designs. You will find a lot of sensors using the resonance frequency in the literature for example, measuring the real part of the permittivity of solid samples such as substrates or 3D printed materials. We have usually values between 3, 4, and 5 that are very low values. And that's very clever. There is also a lot of works measuring the purity of oils such as olive oil or sunflower oil or frying oils by tracking the changes in the resonance frequency. That's also very clever because the permittivity of those oils are between 3, 4, 5 and values very low. So that's good option in those cases, but it's not a good option in our case. So let's have a look in the other picture and see what happens. Okay, this is it. This is the result we were looking for. This is the good option, indeed. Look at the picture. Look at the curve. Look at the slope. It is a sharp slope. So we can be sure that a very small change in the loss tangent of the solution due to a change in the glucose concentration will be seen as a noticeable change in the quality factor. So this exercise is an exercise everyone should do before starting designing any sensor. So run simulations with a wide range sweep of several parameters, see all the metrics that you can analyze, and see which is the most convenient one for your particular sample. And then you can run optimizations so that you optimize the slope of the curve. For example, please note that I cannot move the circle. The circle is a property of nature. I cannot move it. But by playing with the previous design, we can move a little bit the curve so that this area may fall into this circle, for example, by changing the permittivity of the substrate, by adjusting some impedances and so on. We can make some movements of the curve. Of course, we cannot make such a big movement here, so this option is discarded, but here we can still make some optimization. I just wanted to put here a graphical example so that we can easily identify which is the good one. And this is the reason why in this lecture I propose the use of sensors based on the unloaded quality factor for the application of glucose measurement. We can see here also from a theoretical analysis. Here we have again a model of a simple resonator, RLC, in which we have included the contributions of the line for each lumped element, but also the contribution of the sample for the capacitance and for the conductance. We didn't include it for the inductance since water glucose solutions are dipolar solutions, so there is no contribution to the inductive part. Now we can compute again the expression for the resonance frequency and the unloaded quality factor. We obtain these expressions and we can apply these simplifications. We can consider that the capacitance of the sample is considerably higher than the capacitance of the line, and the inductance of the sample is considerably higher than the inductance of the line. These assumptions indeed are consistent. First of all, because from the previous slide, we know that the real part of water is very big. So the capacitance associated to water will be very big. And also we are designing ourselves the sensor, so we can design it so that we have a low capacitance associated to the line. We can force these expressions to be true. Okay. If we consider these approximations, here we can remove the capacitance of the line here and here as well. And in parallel, if we consider the definition of the loss tangent of the sample, the imaginary part over the real part, which is the conductance of the sample over the resonance frequency times the capacitance of the sample, here applying these simplifications, we will obtain the inverse relationship that we have here. So we can conclude that into this expression with the approximation that we applied, that the unloaded quality factor is directly related in an inverse law to the loss tangent of the sample. So it is immediate translation, the variations of the sample to the variations of the unloaded quality factor. The relationship is inverse as logical, since an increase in the losses should lead to a decrease of the quality factor. And also, we know from other studies that for water glucose solutions below 15 gigahertz, if we have a change in the glucose concentration, exactly the same change in the glucose concentration will lead to an increase, a positive increase of the imaginary part of the permittivity and the negative increase of the real part of the permittivity. Being the loss tangent defined as the quotient between these two parameters, if they are changing with opposite trends, the quotient is changing in a more noticeable ways. So the changes in the loss tangent will be more noticeable, which means that the changes in the quality factor will be more noticeable. Both ways, regardless on the approach you take, both ways lead to the same conclusion: the interest of having a measurement based on the unloaded quality factor. So thanks to this principle, we can just make a brief summary here, and then we will see some examples of successful studies. As a summary, the main advantages of microwave resonating quality factor-based sensors for biomedical applications include significant penetration depths in living matter. We will be able to make measurements in vessels, in blood, without entering into the body, and we will be sensitive to variations in the main relaxation processes of aqueous systems. Also, we will have the non-invasive capabilities and the general advantages of microwave circuitries that is compatible with planar technology, ease of integration, small sizes, cost effectiveness, and so on. And in the current landscape, these sensors are facing two main challenges. First of all, sensitivity, and secondly, the selectivity. The sensitivity is always important. We are talking about sensors. Of course, we need sensitivity, but particularly for biomedical applications, because the amounts that we want to measure are very, very, very small. Please note that the amounts of glucose in blood are very, very small, and also for other components. So we need a very high sensitivity. However, I did not select this as the main challenge, because the last years we saw some works achieving unprecedented sensitivities. There are published recent publications showing several techniques such as, for example, coupled resonators. Or I did not talk about the phase in this lecture to make the focus a little bit, to make the focus not so broad, but using the phase of the S11 parameter or S1 parameter and controlling the phase slope and doing some losses engineering, there is also possibilities to achieve great sensitivities. So this is always a challenge. It is always interesting to study the sensitivity, but in my humble opinion, the current real challenge for these sensors is the selectivity. And let me explain this. Of course, you want your sensor to be sensitive to glucose. You want that when there is a change in glucose, your sensor has a change in your response, but you don't want to see a change in your response when there was a change of another component. And for biomedical application, there will be changes of all the components in blood. So you want your sensor to be selective only to the changes in glucose. And this is particularly difficult with microwave sensors. Not impossible, but difficult. So this is, in my opinion, the main challenge for the next years. We will see some examples at the end of the lecture. And now, based on the principles that we described, there was some works that proved the effectiveness of these sensors. Here we can see one of the first works with very simple resonators, open loop resonators at different frequencies to analyze which is the most interesting one, just the sensor connected to the VNA and with a micropipette filling the sensor with the container with water glucose solutions. The results really showed good linearity for the changes in the quality factor for each glucose concentration, good measurement capabilities at different frequencies. The highest sensitivity was obtained for the sensor R2, which was resonating at 7.5 gigahertz. Sensor R3 was resonating at a higher frequency, but due to the size requirements, the sample holder was very, very, very small. So this result is indeed interesting because even though if the sensor did not achieve the highest sensitivity, it was able to make measurements with very low error, with good linearity in very, very, very small volumes, like 1 microliter volume. We made these experiments with water glucose solutions and also with human blood solutions, and we obtained similar results. So the sensing paradigm was proved effective and interesting. Going a step beyond, we wanted to analyze which are the contributions of the value we obtain for the unloaded quality factor with each measurement. We can define two types of contributions. The contribution that comes from the conducting parts, from the copper lines, and the contribution that comes from the dielectric parts, the substrate and the sample. The contribution from the conductor part, well, we cannot change it. It depends on the conductivity of copper. And indeed, if you use good conductors, such as copper, this value will be very high, which means that this fraction will be very low, so very close to zero, which means that the contribution for your unloaded quality factor will be only related to the contribution of the dielectric parts. And again, the contribution of the dielectric part can be divided into two contributions, the contribution coming from the substrate and the contribution coming from the sample. Here we would like to say the same. We would like to say that this value is very high so that this fraction is close to zero. However, it's not straightforward. So for high sensitivity of unloaded quality factor to only the changes due to the sample, we need to force that the value of the contribution of the substrate to the quality factor is very high. This means using very low loss substrate. And in a new study, we decided to use the lowest losses substrate that we could find, that is air, in an inverted microstrip approach. So we developed a special fabrication in which the conductive part in orange, the copper, was etched in the bottom of a certain material. Since we had to go for a different fabrication as material, we selected a biocompatible material that was certified for its use in medicine. And we no longer used usual copper. We used a special copper that is also certified for its use in biomedical applications, which means that the conductivity is not as good, but okay, we can compensate with the air in the substrate. So we etched the resonator and the input-output lines in the bottom of the biocompatible material. Then we fabricated two transitions for the input-output ports that are far enough from the resonator. The transitions are fabricated with usual micro drilling machine and a usual substrate. And then we included an aluminum ground plane holded with 4 screws, so that the assembly leads to a configuration of inverted microstrip in which here in orange we have the resonator and the input-output lines. We have air in the middle, and then we have the aluminum ground plane. We fabricated the piece so that the sample holder and the sample were entering into this virtual substrate. With this sensor, we can see it here in real life. With this sensor, we made measurements with 2 different glucose range, a large range of concentrations that is interesting for industry applications, such as the production of drinks, spirits, sodas, and so on, and a low range of interest only for diabetes purposes, the usual ranges that a diabetic person will find in its blood. And the results were very good for both ranges, good linearity, low error, very good repeatability. Even we could run a medical test, a clinical test, which is called the Clark error grid. That is a conventional test applied for glucose sensors for the treatment of diabetes, with very good results, with majority of points in region A, which is the safest region. So we were happy with this fabrication. And now, just to show you that all the previous studies, all the experimental part was done in laboratory with a very costly VNA, but this does not mean that the technology is very expensive. We can propose fabrication for portable units with usual circuitry that is not really expensive. For example, here we have one possible implementation for a portable device. Everything starts with a microcontroller unit, which is connected to a screen just for graphical interface. Then one of the analog outputs of the microcontroller units generates a ramp voltage signal that is driven to the VCO here, the voltage control oscillator. As a result, at the output of the voltage control oscillator, we have a chirp signal that is a sinusoid signal with increasing frequency from low frequency to high frequency. The signal is filtered in order to avoid harmonics, and then with a directional coupler, we have a copy of the signal. One of the copies of the signal with an attenuator is driven to the RF detector, and the other copy of the signal is driven to the device under test. That is the connection for the sensor. The signal is driven to the sensor, the measurement is made, and the signal returned from the sensor is driven with another attenuator to the RF detector. The detector makes the subtraction between the original signal and the signal coming from the sensor, and in the gain output we have the contribution only from the sensor. Here we have the response of the sensor that is driven to the microcontroller unit for digitalization and processing. Simple electronics and not very expensive. Now let's talk briefly about modern techniques in the last years for, in this case, sensitivity boosting. I will focus only on coupled resonators for brevity, although there are other interesting techniques as well. Here we could show the benefits of using two mutually coupled resonators and putting the sample in the coupling region. If we design the system so that all the contribution of the coupling goes only in the odd mode, we can have very noticeable changes of the resonance peak of the odd mode, both in resonance frequency and quality factor. Particularly, here we have the implementation, and well, the working principle is very simple. A change in glucose concentration leads to a change in the complex permittivity of the solution. This is seen as a change in the coupling properties, and this is seen as changes in the response of the sensor. In comparison with the same study, with the same resonator in the single resonator case, we saw an increase of almost 300% of the sensitivity of the quality factor. And now let's talk about what is, in my opinion, the main challenge, the selectivity improvement, the ability to discern the variations of glucose from the variations of other components. Here, I cannot select a good option. I mean, there is no good option. There are different approaches that are being researched right now, and I will just give very short hints about some of them. One approach implies the different phenomena sensing. This is a physical approach, and we want to separate different physical phenomena. Here, we used two couple resonators, but this time it was not optimized for sensitivity gain, but we wanted to have a broadband measurement, more like a filter, because we were interested in having measurement points at low frequencies and measurement points are high frequencies. And this sensor was tested with different kinds of solutions. Here we have an example with solutions, ternary solutions with water, salt, and sucrose, which is a type of glucose. And in another study, we could also separate the contribution of sodium lactate and glucose. And the working principle is that you should make a broad measurement so that you can have information at low frequencies that is unique to one of the components, while the other one is not varying, and information at high frequencies that is unique to the other component. This can be defined taking several measurement points and several measurement metrics and considering the concentrations of each one of the components. And then from the experimental response, you can feel the frequency points you took and then bandwidth and so on, and then compute the inverse solution. As a result, we could effectively separate the effects and obtain the two concentrations of the two components while they were varying simultaneously. However, it is important to say that this sensing approach makes the driving electronics more complicated because now we have broadband measurement, more frequency points, and the cost and the complexity may increase. Now let's go for an analytical multi-parameter sensing. Here we see only a conceptual example in which the measurements were made with solid samples, just solid material under test, just as a proof of concept. Here we have the sample sandwiched between two substrate boards in which three resonators were etched so that they were coupled in a space coupling, okay, going from the upper board to the lower board and so on and so forth. This allowed us to measure three frequency points. I want to say that this approach is not so narrow band such as the previous one. The frequency points can be close together. And from these three resonance frequencies, we can compute different indicators of the response, the three resonance frequencies, three bandwidths, three maximums, and so on and so forth. And from these indicators, we can compute the original properties of the material under test. In this example, there were three properties changing at the same time in the material under test that were the real part of the permittivity, the loss tangent of the permittivity, and the thickness of the material under test. With extensive simulations, we analyzed all the possible combination of all the parameters that we could retrieve, including a global parameter of the global response, that is the bandwidth of the global response, and then for each particular peak, several parameters, resonance frequency, maximum of amplitude, bandwidth, and quality factor. From these simulations, we ran an optimization study and selected the three indicators that yielded to the highest combined sensitivity to the three properties of the sample. We defined the fitting functions and we solved them with the real measurements to obtain the three parameters for each sample, the real part permittivity, loss tangent, and thickness for each sample. As we can see here in the results, the linearity was very good for the three parameters at the same time with very good fittings in all cases, good accuracy and low error. This is the original work only for solid samples, and after that, very recent works have demonstrated the use of this multi-parameter approach for selective glucose detection using sophisticated deep learning techniques or machine learning processing. As long as the system gets more complicated, there are more elements varying at the same time, and liquids are more complicated than solids. When the complexity increases, the computational load of this model becomes intractable. This work was fully made analytically, but when the complexity increases, the use of these techniques, machine learning, deep learning, and artificial neural networks, and so on, really makes sense. And that was all. Thank you very much. I hope you enjoyed this lecture. It was a pleasure for me. I am Gabriel Juan from Miguel Hernández University of Elche. Here is my contact for any doubts or for any proposals. Why not? And please, before we finish, let me show you just one more thing, because I want to finish with a small present for you. I am stopping to share the screen in this moment. I will share a link through the group chat.
Carlos, are you still with us? That does not seem to be the case. Maybe hopefully this was just the wrong button. Maybe we wait for a second.
Hello?
There you are again.
Do you hear me? I had a problem that the application reloaded. So
Okay.
did you see the full lecture?
Yeah, the lecture was fine. You were just about to
Okay.
check the
Does everyone hear me now? In the moment I stopped sharing the screen, something went bad. Okay, but
Okay.
I just wanted to finish by sharing with you a small present. I am sharing a link through the chat for everyone. And now please let me share again the screen, because very recently we published, we should see my screen right now. Do you see my screen?
Yeah.
Okay, very recently in the IEEE Instrumentation and Measurement Society, we published a tutorial website. So here in the link I shared with you, you can access a tutorial to this lecture with a more practical approach, with its 2 videos that you can see them in YouTube. You can play them as many times as you want. It's fully for free. And here in these videos, I explain how I run these simulations, how I obtained the results I showed you with a more practical view. So today we discussed the theory, and here you have the practice. And that was all. Now I stop sharing, and if someone has any question, I will be pleased to answer.
Yeah. Thank you, first of all, Carlos, for this very, very interesting talk. So I really like how you managed to span the whole band from the very fundamentals to really close to application scenarios where you also have considered the electronics and so on. So to all our participants, you should be able to see a Q&A button at the lower end of your Zoom window. So feel free to enter anything there, what troubles you or where you are interested in. You can also use the chat window if this is more convenient to you. So in the meantime, there has already been an initial question entered, and maybe, Carlos, I just read it to you, and you discuss the answer. So there was a question, or basically 2 questions. The first one is, the experimental setup shows an in vitro setup. What is the advantage of in vitro microwave sensors as opposed to conventional electrochemical sensors?
Sorry, I didn't hear very well.
Yeah, sorry. Carlos, maybe can you also see the Q&A panel at the lower end? Maybe that's, if you can read it at the same time, that's maybe more easy.
Yeah, question and answer, but I don't see any questions.
Okay. Yeah, then I just read it. So basically it turns down to what is the advantage of microwave sensors in contrast to conventional electrochemical sensors?
Well, the main advantage is the non-invasive capability. As long as chemical processes are involved, you need to direct touch the liquid or the sample so that the reaction occurs. Microwave sensors have, in my opinion, the main advantage is the non-invasive capability, non-destructive capability, not only for biomedical applications, also for industry applications. The sensors are also used in quality control for the production of certain liquids. And its main benefit is that you can attach the sensor to the tank and make measurements through the wall of the tank without contaminating the tank or taking out a sample of the tank and stopping the production the production process. Other advantages include general advantages of microwave, such as easy of implementation, mass production, cost effectiveness. They don't need disposable parts that are only one use part and so on. And then for biomedical applications, well, just only the non-invasive capability is a winning advantage. Of course, there are problems for real implementation that we need to solve, but research is open for that.
Mm-hmm. So the second part is, I guess, more related to the biomedical aspect. When applying this concept to an in vivo measurement, how does this measurement apply to the lack of interstitial glucose levels behind blood glucose?
Yes. The lag between interstitial glucose and blood glucose is considerable. It's about 15, 20 minutes, depending on the individual. However, in my opinion, it is a useful, complementary information. Diabetes is more than blood glucose, okay? The problem is not only having a high level or low level of blood glucose. The problem is how your cells are accessing glucose. So there are specific complications in diabetes that can only be seen by measuring interstitial glucose, because there is a problem, which is a glucose shock. When people is close to a glucose shock, that people have good acceptable glucose level inside the vessels, but they have very low glucose level in the interstitial fluid, because the pancreas is more or less working and they are controlling the levels, but there is a problem with the insulin in the last step when the glucose, the cells are taking the glucose and cells are not feeding with glucose. So honestly, microsensors are the only one that can detect these kind of things. Not even the chemical sensors, because you cannot have a drop of interstitial fluid. And then, as you said, the measurement with a microwave sensor will not be inside the vessel. It will be in the first layers of the skin. So you need to know that. You need to know that the measurement you are obtaining is delayed 20, 15 minutes. For real life treatment, it can be acceptable or not, depending on the severity of glucose. But it could be also, as a complementary information, really interesting. And well, now there is always a balance. Okay, there are several technologies that we can use. The conventional technology implies pricking the finger, getting a dropout, making the measurement, and so on. The experience is that this is done regularly the first years that someone is diagnosed with diabetes. But when you have been living 20, 25 years with diabetes, you start to feel more relaxed, and you have no fingerprints, so you need to make the puncture in a different part of the body. You forget to do it, and so on. So looking for a more comfortable measurement principle, even if it's a little bit delayed, could help this stage of the disease. In the end, having an immediate measurement that people will not do or will not do regularly, or having a comfortable measurement that is delayed 20 minutes, depending on the severity, could be interesting.
Okay. Yeah, there's another question, rather technical, let's say. Can you clarify why you work in transmission mode with your resonator?
Okay. It's a question from Professor Martin. Hello. Indeed, for the sensing principle, you can work in both modes, in transmission or reflection. It depends on more how you optimized the response for a particular sensor. Since our experiments, our works were always very experimental, we wanted to save all the parameters, but there's no gain from the quality factor, from the theory, from the quality factor definition. There is no gain in computing the quality factor from the S21 or the S11 transmission mode or reflection mode. It's easier to define from the S21 if it's not enough, if it's an absorption mode, because it's easier to define the fall of the 3 dBs. When you have a maximum, it's easy to define where is the fall, the 3 dB fall from the maximum. When you have a minimum, there is a correction you need to apply, and we have used it sometimes, and it's not a problem. But it's more computation. So again, it's a new source of error and these kind of things. I know personally Ferran, and I know that they were quite often in reflection mode. I said very briefly the approach of using the phase of the scattering parameters that leads to huge sensitivities. But well, I need to focus the topic of the talk, because I have only 1 hour, so I cannot touch all the topics. The sensors using it's reflection mode for obtaining the phase of the S11 have one particular benefit in addition to the sensitivity, that is the cheapness of the driving electronics, because in that case you only need one measurement point, and you don't need to make the strip of the frequency with the VCO and so on, because you only need to measure the phase at one point. In our case, we do research. I mean, we just explore what happens. So we wanted to explore how we could make sensors based on quality factor, based on the previous simulations that we had made and the variations of the loss tangent and so on. So we decided to go for transmission mode because it was the conventional computation of a quality factor or of a bandwidth that you required for the quality factor is made from a transmission. I don't know if this answered the question.
I'm sure, I guess that will be fine. I have a question myself. So you showed very nicely this conceptual study in the beginning regarding the dielectric properties of water and the losses, for example, where you said, okay, let's go for the losses because it's more convenient or it gives us better sensitivity. And you argued that the high dielectric constant of water at 9 gigahertz hinders a good evaluation. Would it help go to much higher frequencies, let's say 90 gigahertz or something like that, where the dielectric constant of water falls down to order of 10, let's say?
Yes, definitely. If you look into the dielectric characterizations of water, I put it a couple of references, and well, there are plenty of them because it's a very wide, very studied topic. It depends on a lot of parameters. It depends on the temperature, it depends on the atmospheric pressure, and so on and so forth. But in general conditions, in normal conditions, in laboratory conditions, the main relaxation peak of water is around 20 gigahertz, a little bit less, like 18, 19 gigahertz. It's not interesting to go exactly to the dielectric relaxation. It would be not a good idea to make the measurement at 18 gigahertz because that's the top of the peak of the losses peak, and maybe you will measure nothing. I mean, you will have only losses, but approaching without reaching, but approaching this peak is always a good idea. I would say that making measurements with a resonator at 16, 15 gigahertz would lead to higher sensitivities. However, in this case, we have practical restrictions because the sizes will be very, very small. And for a laboratory setup, we also need a container and a pipette and so on and so forth. So we went to the biggest size we could produce considering all the constraints. That was 9.2, 9.5 gigahertz. I would say that the most desirable, from the theoretical point of view, the most desirable frequency would be around 15, 16 gigahertz. And it would not be interesting going beyond the dielectric relaxation. Going beyond 20 gigahertz, it would by no means be interesting because the curve will flatten at that point.
Okay. Yeah. Thank you for that. There is another question from the audience. This topic has been researched a lot. One of the challenges, as you said, is the selectivity. The sensor will be placed on human skin, so the thickness of skin, sweat, other substances in blood will make it look like glucose has changed. Do you think this can be solved accurately enough for it to be the only sensor needed?
Okay, I cannot predict the future, of course, but if I had to bet, if I had to put money, I would say that if a solution is reached, it will not be a universal solution. I mean, the sensor will require individual calibration. That's for sure. I mean, in my opinion, if we achieve a sensor that is working well, that can be used in people and so on and so forth, at least you will have to live 1, 2, or 3 days more pricking your skin, taking blood of your skin and making measurements parallel with the sensor to calibrate for your thickness of the skin, for the color of your skin, for the composition in terms of dead skin, in terms of fat, in terms of any other things in the skin, and so on. Individual calibration, for sure. And then I think that it's difficult to predict, but once we achieved acceptable sensitivities, the efforts will be on increasing the amount of information available. Having 3 resonators, 4, 5, I don't know, having several frequency points, having other technologies in parallel than microwave, such as optical, for example, having several information sources, non-invasive information sources that can be combined with a specific computational approach for solving all the relevant parameters and obtaining the glucose concentration. And there is one more thing I would like to highlight in this answering to this question. Glucose will change daily. I mean, every few minutes in diabetic people, and there will be other components in blood changing as well. That's normal. However, there will be no component changing as fast as glucose in a diabetic person's body. If the sensor is calibrated, it is calibrated for your current levels of the rest of components. And then from that point, your glucose will change in 15 minutes, in 1 hour, in 2 hours, but the rest of components, in the absence of other diseases, the rest of components should be the same or with very low variations in the rest of in this time. It is likely that the sensor will need to be calibrated at the first use and maybe recalibrated monthly, for example. Okay. But anyway, it will be even more comfortable than the current systems. But yes, this is the main challenge. I don't see it as a bad aspect. I mean, as a researcher, I see it as an opportunity. This is our opportunity. So this is the new problem we need to solve. Let's start writing projects. Let's start raising funds, and let's start working on that.
That sounds like a good answer to that. Yeah, I guess up to now there are no open questions. So the last chance for you out there. If not, I'd like to take the chance to thank you again here, Carlos. It was very nice having you. I think
My
also
pleasure.
from the response that we got that yeah, your talk really made an impression, and yeah, thank you for being here, and yeah, to all in the audience, thank you for joining us in this webinar, and yeah, looking forward to see most of you again, hopefully in our next event. Thank you.
Thank you to you all. I hope it was useful for you.
Yeah, really good. Thank you. So I'll now close the session, and yeah, bye-bye.
Goodbye.